From Himalaya to outer space, humans have never stopped their great exploration to the unknown world. Satellite, for example, is one of the commonly used tools to assist this. However, it requires effective navigation to provide this accurate location in space. That's what we're going to talk about today: navigation in space.
To determine and navigate an object in space, first, we need a coordinate system.
The most famous 3D Cartesian coordinate system gives us an idea of using number lines to represent space. Once the origin is determined, three axes x, y, and z, which are all perpendicular to each other, start from that origin point and create the 3D Cartesian coordinate system. The relative position of an object can be shown by x, y, and z numbers. Another basic coordinate is polar system, also known as angular system. It uses angle and distance according to the origin to locate object on a 2D plate. However, an additional of another angular dimension produces a spherical coordinate system. The longitude and the latitude system is a spherical system, which used to simulate the Earth's surface. Based on the celestial equator, the Earth is divided into many latitudes. On the other hand, based on the prime meridian, the Earth is also divided into many longitudes. With the longitude and latitude system, any object on the Earth's surface can be determined with two angular dimensions. But if we want to find the relative location of a star, the celestial coordinate system can be used to catalog stars. It is also a spherical coordinate system where the origin becomes Earth this time. All the stars can be thought of as being on an imaginary sphere. Angles measured north or south from the line of the celestial equator are called the declination and are measured in degrees. This is similar to lines of latitude. The longitude equivalent is called the right ascension. This is measured in hours, which means the time that the star needs to travel from areas in the sky.
Usually, a Cartesian system is used to define the location of a spacecraft. But any other coordinate system also can be used with different origin and different references. It all depends on where the spacecraft is in relation to the Earth and why the location is required.
Initial navigation is when the position of the vehicle is calculated without the use of external observation or equipment. Generally, an initial navigation system uses gyroscopes and accelerometer to maintain the estimate of the position, speed, and the altitude of the vehicle, which could be a land vehicle, aircraft, or even a submarine.
First, let's have a look at the basic accelerometer. They have two fundamental parts: a housing attached to the subject, whose acceleration we want to measure, and a mass that attached to the housing which can still move. Here is the spring with the heavy metal ball. If we move the housing up, the ball will lie behind and stretching the spring. If we measure how much the spring has been stretched, we can calculate the force of gravity. You can easily see three of these can be turned in orientation of the three-dimensional objects. Well, the y and x-axis are parallel to the ground. Only the ball in the x-axis shows the spring extension. Turn it to the another side, so the z-axis point up, and only the accelerometer along the spring in the z-axis stretches. Normally, chips are used to measure the accelerations which is more complex than the simple ball and spring model. It is the same fundamental elements inside the chip, and the engineer created a tiny accelerometer with silicon. It has a housing fixed to the aircraft and a core micro section that can be moved by force. That's a seismic mass, equivalent to the ball. The spring in this case is the flexibility of the thin silicon attached to the housing. Equivalently, if we can measure the motion of the center section, we can detect the change of the orientation. Just see how that's done if zooming the 3 of the fingers in the accelerometer. The 3 fingers make up the differential capacitor. That means that if the center section moves, the current will flow. If you have ever played with the toy gyroscopes, you know that this cannot stand for a second when it is not spinning, but it will perform all sorts of interesting tricks once spinning up. They can stand on the table, balance on a string, or on your finger, or even stand on the string. This all because of the gyroscope has a great ability of motion resistance about the spinning axis. Here is a gimbal initial platform. A gimbal is a rigid with a rotational bearing for insulating the inside of the frame for external rotations about the bearing axis. At least 3 gimbals are required to insulate the subsystem from the host vehicle rotations about 3 axes, typically labeled roll, hitch, and yaw axes. The gimbals in an initial navigation systems are mounted inside one another. Gimbals and torque servos are used to nail out the rotation of the stable platform on which the initial sensors are mounted. So, if the aircraft rolls, electrical sensor and contact connect to the gyro, sending information to the pilot about the aircraft orientation.
You may ask, since initial navigation can be so accurate like that, why do we need external reference after all? Here are the reasons.
Even with most accurate instruments and highlight calibration, cumulative errors will add up, and these errors can be disastrous to a spacecraft. This way, the external references are needed. External references regularly realign the spacecraft by determining where the spacecraft is pointed, how fast it's turning, and how speed is changing. There can be different types of external references according to how external data is collected. Firstly, external data can be obtained on board in onboard system, where the sun or any other particular star is used to help position the spacecraft. While in an Earth-based system, data is collected from radar or optical tracking or even a global positioning system. Okay, here let me elaborate a few more commonly used external references. First of all, sun sensor, which obviously uses the sun as reference. The sun has been used to assist human navigation for thousands of years and will continue to be used in space. Here's one picture of the sun sensors. There are mainly 3 types of sun sensors: presence detector, analog sun sensor, and digital sensor. Presence detector only monitor if the sun is in the field of view, so that spacecraft knows where it's pointing to avoid the sun's radiation or make full use of the solar energy. Analog sun sensor provide a continuous output with a function of sun angle. In other words, angle the light from the sun hit the photocell in the instrument. In terms of digital sensors, it produces an encoded discrete output that is measured by sun angle function. The other type of external reference is star sensor. Look, here's the star tracker which is built in the star sensor. The built-in star tracker is a very small digital camera which takes digital pictures of the stars and then compare the image with star catalog in a database. In this way, the orientation or attitude of spacecraft can be calculated. You might ask how many stars we need to determine the position of a spacecraft. Well, the answer is 2. This can be illustrated by this diagram. Star 1 can only determine the orientation of the spacecraft, but when another star is imported, the spacecraft can be positioned as it is right at where the 2 lines intersect. Did you know which star is commonly used in navigation within solar system? Yep, it's Canopus. It is used as it is easy to be detected and distinguished from other stars. Look, here he is. Well, now come to the third type of external references: Earth or horizontal sensor. Here are the picture of it. An Earth sensor is basically a thermal device which uses infrared camera and a telescope to determine Earth's horizontal and calculate vector to Earth's center, as can be shown in this picture. It is less accurate compared to other types of sensors, but costs less and is very reliable. The fourth type of external reference is Global Navigation Satellite System, GNSS. The Global Navigation Satellite System use cases are US GPS, Russia's GLONASS, US Galileo, and China's Beidou. Take GPS as an example. We might think it only navigates users on Earth like us, but it can provide latitude, longitude, and altitude to users on lower orbits, while geosynchronous satellite has the same orbital period geosynchronous satellite work. As each GPS satellite broadcasts a beam which is slightly wider than the Earth, geosynchronous satellite can receive signals from it and analyze data to determine position of itself. These are the commonly used external references. External references, as important tools to assist initial navigation, help provide more accurate positioning to satellite, giving information on its orientations, velocities, and many other important parameters.
There is an interesting phenomenon coming up with Albert Einstein, that if two people carry the same watch and one people stay on the Earth and another travel with a spacecraft in the universe, we will find the person in the universe will have a slower watch than the people on the Earth. This phenomenon, aka time dilation, and that will affect the navigation on the satellite.
For example, if two spacecraft is traveling in the universe up-down with same speed, which equals to the speed of light, the upper spacecraft have a laser blast in the bottom, and the downer one get a mirror on the top. When the blast fire a laser, the laser will reflect between two spacecraft over and over again. But if these two spacecraft flying through an observer, say David, who's standing on the planet, what David will see is quite different, because he will see the motion of the laser will move like a triangle. That's because the observer is still and the motion of the laser should add up shape motion. And now the question comes. According to the theory of Einstein, the speed of light will never change, which means the speed of laser in these two situations is totally the same. But light in the second situation moves more distance because it is moved like a triangle, and David will get a longer time of the laser reflect once than the people seeing from the spacecraft. Now this phenomenon is called time dilation. Time dilation could slightly affect the navigation because the time difference between the observer on the Earth and satellite itself. But in nowadays, this error can be calculated and analyzed to make sure the navigation will be as accurate as possible.
This brings us to the end of our topic today, navigation in space, one of the most exciting and fascinating areas of study nowadays. In this video, we first introduce coordinate system. We then talk about two essential systems that are used to assist positioning of spacecraft: initial navigation system and the position fixing system, or so-called external references. Although combined use of both systems can provide accurate position for the spacecraft, we still need to consider the effect of time dilation. Across the sea of space, the stars are other songs. There will never be an end to human space exploration, and navigation itself will continue its important role in this great and endless mission.